Hello friends, in the previous lecture we saw that the sampling theorem enables time division multiplexing. This time division multiplexing gives rise to an impairment that we want to avoid known as crosstalk. This crosstalk is caused because of the band limitedness of the channel. A band limited channel can be thought of as offering high frequency limitation as well as low frequency limitation to the signal which is applied to it. In this lecture, we will try to study the high frequency limitations offered by the channel to the message being transmitted. Thereby, we'll try to study the amount of crosstalk caused because of the high frequency limitation of the channel. Let us recall that the communication channel acts as a band pass filter, and a band pass filter will reject or attenuate high frequency components as well as low frequency components and will allow only the frequency components in a given band, which is the bandwidth of that filter. An ideal band pass filter will have sharp cutoffs at lower cutoff frequency and upper cutoff frequency. So there is a strict pass band and strict stop bands, but there is no transition band. However, a practical low pass filter will have the frequency response as shown here with a pass band, a stop band, and there is also a transition band. A communication channel acts as a practical band pass filter, and for convenience of analysis, that can be thought of as composed of an ideal low pass filter. An ideal low pass filter will have the characteristic something like this, and an ideal high pass filter which will have the characteristic something like this. So it is convenient to model our band limited channel as a practical low pass filter for studying the high frequency limitations, because it is attenuating the higher frequencies beyond some particular frequency. And then to study the effect of low frequency limitation offered by the channel, we will model the channel as a high pass filter in the next lecture. So let us once again recall what is crosstalk and why is it caused. Remember that the pulse that we are transmitting after sampling, the pulse is a time limited pulse, and a time limited signal is always band unlimited. So when this band unlimited signal is passed through a band limited channel, that band limited channel curtails the higher and lower frequency parts of the pulse and makes the pulse band limited. So now we have a band limited pulse at the output of the channel, and now because the pulse has become band limited, it has now become time unlimited. And this is what we call pulse dispersion. If we were transmitting only one pulse, this time dispersion would not have caused any problem. However, we are transmitting several pulses one after another, and all those pulses get time dispersed because of the band limitedness of the channel, and therefore these time dispersed pulses overlap, causing a distortion that we call crosstalk. Crosstalk and another phenomenon, intersymbol interference or ISI, are similar. But the difference is that the crosstalk, this term is used when we talk about the interference or influence of one pulse of a message with a pulse of some other message signal, whereas intersymbol interference is the interference between two pulses of the same message signal. So I hope this difference is clear. Let us now study the high frequency limitation of the channel by modeling the channel as a low pass filter. The simplest low pass filter that we can think of is a simple RC circuit in this fashion. let us show that it acts as a low pass filter. The frequency response of this simple RC circuit can be written directly as 1 over 1 plus j 2 pi f RC, where RC is the time constant. So we can directly just write tau C as a time constant, where tau C is equal to R into C. The magnitude response can be written as 1 over root 1 plus 4 pi square f square tau C square. Clearly, when we sketch it, when f is 0, mod hf is 1, and as f increases, this magnitude resembles the characteristic of a low pass filter. There is some cutoff frequency 1 by tau C, where the magnitude of hf becomes 1 by, so this is 1 by 2 pi tau C, and that is the cutoff frequency where the magnitude becomes 1 by root 2. So this is a practical low pass filter, RC low pass filter. So that means if we apply our signal, the pulses, as the input VIT, we can study the effect of crosstalk by studying the output. Let us see that now. So this is a depiction. This is the first pulse that we have applied as input. It's rectangular in nature. The pulse duration is capital T and the pulse amplitude is V. At the output, this is the output VO. The capacitor, when this pulse is applied at the input, the capacitor charges, and the charging time constant tau C is much smaller than the pulse duration capital T, and therefore the capacitor charges to its full value within T, and it acquires a maximum value here. And then when the input pulse takes 0 volt, then the capacitor starts discharging, and it follows this exponential form of discharging, and this discharging continues, and it occupies the second time slot where we are transmitting the second pulse, and there is an overlap between the second pulse and the spreaded pulse from the first time slot, and this overlap amounts to what we call the crosstalk. We will try to mathematically analyze and see the amount of crosstalk. So this crosstalk can be measured in terms of what we call the crosstalk factor. So the crosstalk factor is defined as the ratio of the area A12 upon A1, where A12 is the overlap area of the first dispersed pulse to the second actual pulse, and A2 is the actual area of the pulse 2. We assume for convenience that pulse 2 is same as in shape as pulse 1, and therefore the area of the second pulse is same as the area of the first pulse. So let's now try to compute this area A12 and A1, which is same as A2. Okay, so A2 is same as A1 and A1 is simply V into T. That is very simple. Let us try to compute A12. We assume that the pulse duration is capital T, and before we transmit the second pulse, there is a time gap. We call this time gap as guard time, and we denote this guard time by tau G. Okay, so at T plus tau G, the second pulse starts, and therefore our overlap also starts at T plus tau G. And what is the equation of this exponentially decaying curve? We know the capacitor discharging characteristic. It is V e to the power minus T by tau C, but it is starting at capital T, so there is a time shift, and therefore the equation becomes V e to the power minus of T minus capital T by tau C. Okay, so I hope this is clear. So A12 can now be computed as the area under this curve from t plus tau g to 2t plus tau g. Assume that beyond this, the overlap is almost negligible. So the equation of this curve is v e to the power minus of t minus capital T. If it had started from 0, so it would be v e to the power minus t by tau c. But because it is starting at t, there is a delay. So there is a shift. So in place of t, we write t minus capital T by tau c. So v e to the power minus of t minus capital T by tau c. And we need to integrate this function from t plus tau g to 2t plus tau g. So we need to integrate it from t plus tau g to 2t plus tau g dt. Let us make a simple substitution here to simplify the computation. Let us put t minus capital T equal to lambda. So we get dt equal to d lambda. And as far as the limits are concerned, when t changes from t plus tau g to 2t plus tau g, it makes lambda to vary from, you can just check, when t is t plus tau g, lambda is simply tau g. And when you put in place of t, small t, you put 2 capital T plus tau g. So 2 capital T plus tau g minus t is simply t plus tau g. So our limits change here and become tau g to t plus tau g v e to the power minus lambda, because t minus capital T is lambda, by tau c d lambda. This is equal to, so v is a constant, we can write it outside, e to the power minus lambda by tau c. When we integrate it with respect to lambda, so we get e to the power minus lambda by tau c upon minus 1 by tau c. So that tau c comes up here with a minus sign. The limits are, it can be simplified easily to get a12 equal to, we had minus v tau c, let me write it once again, minus v tau c e to the power minus lambda by tau c e to the power minus lambda by tau c, and the limits were from tau g to t plus, yeah, that's correct. So let's now simplify it. So minus v tau c, inside bracket we write, in place of lambda we are writing this, so e to the power minus of t plus tau g by tau c minus e to the power minus tau g by tau c. Now from here we can take minus e to the power minus tau g by tau c common. That minus will make this minus plus, okay, and we get, now note that we had mentioned here that this tau c is much smaller than t. Mention it here again. Tau c is much smaller than t, and therefore this t by tau c is a large quantity, and with a negative sign this term becomes very small and negligible. And what we can do is we can approximate a12 to v tau c e to the power minus tau g by tau c. And now we can compute the crosstalk factor. The crosstalk factor we had defined as k equal to a12 by a2, and because a2 is same as a1, our crosstalk factor k is equal to a12 upon a2, which is a12 upon a1, and that is equal to, a12 is v tau c e to the power minus tau g by tau c divided by a1. What is a1? A1 is very simple. A1 is just the area of this rectangle. So height is v, width is t, so v into t is the area. So this is v into t. The v here cancels, and the crosstalk factor is obtained as K equal to tau C by T e to the power minus tau G by tau C. So note that the crosstalk factor, the amount of crosstalk, depends on tau C, the time constant, the pulse duration, capital T, and the guard time tau G. Now we cannot do anything about tau C because it is a channel characteristic. But this tau G and capital T, we can decide. See, if this tau G is taken to be much larger than the time constant, then this term becomes negligible. However, if we increase tau G to a large extent, then we'll not be able to embed pulses from many signals, so the time division multiplexing will get affected. So there is always a compromise, but in a given situation, for a tolerable crosstalk, we can always decide what should be tau G and what should be capital T, the pulse duration. They summarized here that when tau G is much larger than tau C, the crosstalk is almost negligible. And for a maximum allowed crosstalk, we can decide the pulse duration and the guard time. So that's all for this lecture. In the next lecture, we will talk about the high frequency limitation as offered by the channel and study the effect of crosstalk there. Thank you.